Hello, so today we are doing this problem called checking that a graph is a valid tree. So the problem says that we have, so we get an undirected graph as input, and we want to check whether it's a valid tree. And so the first example is this one, where we have 0 connected to 1, maybe let's visualize it, so 0 connected to 1, and then 0 connected to 3, like that, to 2, and then 0 connected to 3, so I don't know how to do that, so let's say something like this. 0 is connected to 3, and we get 1 is connected to 4. So you can see here that this is kind of a tree because there is no cycle, and we have 5 nodes and they are all connected, and that's essentially a tree. Not necessarily a binary tree or a specific type of tree, but it is a tree. A tree is like a tree should have some properties like all vertices are connected, all its vertices are connected. So essentially this can be interpreted into, this is equivalent to two things actually. So this means that there is one connected component, and it also means that if there are n vertices, it should have n minus 1 edges, because if it's more than n minus 1 edges, that means that there is at least one of them has to be connected to another one two times or multiple times even. But if it's less than n minus 1 edges, that means that there was certainly a vertex that was left without being connected to anything, because otherwise how can it be n minus 3, for example, edges, you know? And so that's one of the properties. And also there is no cycle, right? Because if there is a cycle, that's kind of also you can deduce it from n minus 1 edges. We need to not be a cycle. So how can we check? So what properties can we check? So we can either check that we have n minus 1 edges, and they are all vertices are connected. Vertices are connected with one component, which is basically means one connected component. Or we can check just that there are n minus 1 edges, and no cycle, right? Because we could have n minus 3 edges, for example, and then for one node it can be like go from one to itself, like say 1 is connected to itself, making a cycle, and then there is 4 not connected because 1 like made 1 extra edge, and so even this property alone is not enough. And so that's also another way to check. So yeah, let's try to implement this then. So the first thing we can try to implement, the first check is, let's just check that we have n minus 1 edges and they are all connected. So this one and this one we can check. So solution 1, just check that there are n minus 1 edges and all vertices are connected. So we can do this with DFS. We can also do it with BFS, and we can do it even with union find, but let's first just do it with DFS. So to do that with DFS, let's call this, let's just make this clear, n minus 1 edges and all vertices are connected. So to do it with DFS, we just need to have a method that visits, And then, of course, we need also to, since we have a list here of edges, so that's not very convenient. So we need to construct somehow a map of neighbors. So let's do that. So we need a map of neighbors so that we can know directly for each vertex what does it map to. So, so for each neighbor, for each vertex, we are going to map first to an empty list. And then these are, we know the number of vertex, and we know it's n, so let's just give each of them an empty list first, and then go through the edges. So uv in edges, and we are going to assign for each. Since it's a non-directed graph, then that means that this u here we can, and v will have as a neighbor u. So, and then after that we need to start a visit from any node, so we may as well start from the first node, which is 0, and so this is the vertex that we are passing, and we can just implement our DFS here. And so DFS would visit the neighbors, so we need to say we can just map to the neighbors, so that map visit to the neighbors. So what are the neighbors of V? Those are neighbors like this. But we can make something clever. So instead of keeping a visited set so that we don't visit a node again, a simpler thing we can do is just use pop to pop this node. And if it's not there, we can just return an empty list. Okay. And then after doing that, and so now after doing that, we need to check the properties that we said, which is n-1 edges. So return that the length of edges, we need to have n-1 edges. So, and the DFS that we did here was just making sure that everything is connected in one single component. So how can we verify that? So since we are popping every vertex we visited here, then at the end, if we visited all of them, that means that neighbors would be empty. Since we pop from the map a key when it's no longer has any elements. We could have also had a visited set and just check that these visited set contain all the vertexes. That's also a valid way to do it. But here, since we just popped every element that had no neighbors anymore, and that was visited, we can just say check that the length of neighbors is equal to 0. And this is just equivalent to checking that not neighbors. That makes it, you can just do it this way. Yeah, that should be pretty much it. So yeah, as I said, you could also keep a track of a visited list and then check at the end for every I in the the set of vertices. We have 0 to n-1, and check that all of them are in the visited set, which means that they are all visited. Yeah, that's pretty much it. So let's run this. So we have a case that is failing here. So why do we have Let's see, why is that one failing? Yep, I think it's because Python 3 maps alone doesn't work. This always, yeah. Basically, another way we could have done this is just by traversing for W in this, and then just called visit in it. But with Python 3 map alone, it's always causes a problem. Okay, so this was using and checking that there are n-1 edges and all vertices are connected. Now another thing we can do is just do also DFS iteratively just to get used to it. So this was using recursive DFS. So just to get used to doing it, I suggest always to try to implement also the iterative, because sometimes some solutions are more natural with it. So let's call this solution 2. And we need to construct the map in the same way, and the check is still the same way because we are still going to use this method. And the only difference now is we are going to use a stack instead. And then, so we are going to use stack. We are going to start with the first node as we did here. And so we are going to do while stack. We are going to do this visit pub and so visiting here would mean just add to the stack the neighbors, right, and do the pub that we did here for this vertex, and so the vertex, what is it? Is whatever we should pop from the stack. So let's say v is equal to stack dot pop, right? And these basically are the neighbors. So to make this easier to see, so let's say for w in neighbors dot pop v. So this is just the default value in case of v is not in the neighbors anymore because we visited it before. So we are just going to do stack dot append w, and this pretty much is all we need to do to make an iterative DFS. And you can notice we could have visited check set and just add it to the visited set here, the vertex v, but since we are popping it from the neighbors, that would make us not visited it again, right? And so I can just run this, and that passes. Cool. Now we did it with DFS. Now let's try to do it with BFS, right? So same thing, all vertices are connected, but this time using BFS. So solution 3. Okay, one thing I didn't do here is I kept the old implementation. So let's just make sure that it's really working. Okay, so it's working. Cool. Now let's implement this with BFS. So same thing, we need to construct the graph in the same way. And then we need a queue for our DFS. So that's collections.dq. And we need to start the queue with 0, of course. Same thing as DFS. And while a queue, we need to get the node by popping from the left, from the start of the queue. And we are going to visit the neighbors of that. So for W in neighbors of V, we are going to need to append. And so one thing we need to do, of course, is remove V from neighbors as we did here so that the next visit doesn't visit V again, right? So let's do pop from V, and just to make sure we don't get any errors, by default return an empty list. And so we need to add these to our queue. And that's pretty much it. And at the end we need to check the same thing, because this is equivalent to, not neighbors is equivalent to checking that the set contains all vertices, and so that should work too. So the only thing that changes with let me just use this so that we can check the new implementation. Okay, so that passes all test cases. So you can notice here DFS can is going to go all the way until 4 and then backtracks and then go to 3 and then backtracks and goes to 2. What BFS will do is go to 0, 2, 3, and 1, and then does from 1 goes to 4. And so it just goes level by level, but at the end it still visits all of them and checks that all of them has been visited, and we check that all edges are n-1 edges. And so whichever type of traversal we do, we will still check that we were able to reach every other vertex from the vertex, starting from the vertex 0. So that's essentially what connected is. Now that we did with BFS, so there is another way we can do this, which is with DFS, but a little bit different. So instead of checking that we have all vertices are connected, we are going to check that we have n-1 edges and no cycles, right? So that's easy to do with DFS. So n-1 edges and no cycles using DFS. So the way to implement, let me just use this like this. So this is solution 4. And so we need a method that checks that there is a cycle. And for that method, we are going to check pass v and something else. I will explain what that something else is later. And now we need the same thing we did here to construct the graph. So this is the same for every one of them. Then after that, this time we are going to have visited set just to make it clear. And then we are going to check if there is any cycle from the vertex 0 or any of its neighbors, then that means we have a cycle and we should return false, because a tree cannot have a cycle. Otherwise, we are going to make sure that the length of edges is n-1, the other part of our condition here. And we are going to check that we visited all of them, which is the same as we did here by checking not neighbors. So how can we check that all of them have been visited? So we can just check I is in visited, so all of them are in visited. That's basically what we are doing for every vertex in the graph, which is just by checking that for I in range n. And now let's fill this checking of having a cycle here. So for a vertex to have a cycle, that means it needs to have an edge from it back to one of its ancestors, because that's for example 4 for it to be a cycle needs to go from 4 to 0. Maybe let me just Google some graph cycles. Yep, so we can see here that for it to be a cycle, it needs, for example, to go from 1 to 2. So there needs to be an edge from a descendant of 2 back to itself. And so there is an edge needed to be from one node to one of its parent, a back edge, basically an edge that goes back. And so let's try to implement that here. So we need a parent, we need to pass a parent so that so for the parent for the first node, let's just note it as -1 because it's nothing. So basically this parent, the way we are, since we are having an undirected graph, the way the parent is going to be useful is because a node is connected to its descendant, and a descendant is connected to its direct parent, because that's the definition of undirected graph. But for cycles, we are now looking for that. That node is not a cycle, because that's just the nature of undirected graph. But if the edge is to a parent that is not the direct parent, then that's a cycle. So we need to pass this parent here so that we can check that the back edge is not to the direct parent, because that would have been just because of this. because it's an undirected graph. So that's why we are passing this parent here. And now for checking hash cycle, when we are doing DFS, so in DFS, this is like using DFS. And so we need to say that we visited this node so that we can check later, make sure that everything is visited. And then now checking the cycle, how can we do that? So, and then also the part of DFS is we need to check all neighbors, the same thing we did here with DFS, with the iterative DFS, and also with the recursive one, is we need to return to visit all neighbors of V. And so we are going to check if W isn't visited. So it means it was visited before, which means it's a parent, because with DFS no node gets visited, like no descendant gets visited before its parent. And so if, let's say 4 here, we are at 1 and we try to visit 4, but 4 was visited before, that means 4 certainly was a parent of 1, because that's the definition of DFS. And so in this case, if W isn't visited, and W is not the direct parent, which is what we said, that means we certainly have a cycle, so we need to return true. Another condition that we may have a cycle is if any neighbor of V has a cycle, then that means we have a cycle, and we need also to do that so that we can add the new visited neighbor to the visited set, or the visited list. So if W is not visited, so it hasn't been visited yet, so it's a normal descendant, and hash cycle of that W returns true, that means we have a cycle, because there is a cycle starting from that descendant. And what is the parent of W? That's just V, because that's the definition here of taking the neighbor of V. And then we are going to return false. Yeah. Oh, true, sorry. That means we have a cycle, so we are going to return true. Now, if we didn't find any condition that says that we have a cycle, that means we don't, so we return false. Okay, so let's run this using this. Okay, so that passes. So this was using DFS and checking that we have n-1 edges and no cycles. Another solution we can try is using checking n-1 edges and connected, but this time using union find. So basically we can check that we have n-1 edges and no cycle, actually, sorry. n-1 edges and no cycles, but this time using union find. So union find, basically what it does is we have, at the start we have sets, different sets, so one for each node. So we have one for 1, one for 2, and each node has a representative or a parent, right? And so what would happen is that, so like this, first they start out each alone with their parent like this, each its own parent. So I'm going to mark a parent with a star, and then we are going to check the edges. So first we check the edge 0, 1, and then, so whenever two nodes are, or two vertices are linked with an edge, we put them in the same set and we pick one of them as the parent. So let's just pick 0. And then we have 0, 2. So we need 0 is in this set, and we need, with the edge is 0, 2. So we need to have this also as the same set because they are connected. And let's leave the parent as 0. And then we have the edge 0 to 3 here. And so same thing, becomes connected, and the representative is still 0. And then we have 1, 4, and so 1 is in this set, so we find its parent using find operation, and so its parent is 0, and so we link the set that we found with this set, and so now we have 4. And so we have now we are done exploring all edges, and we have only one set, and we didn't find at any moment. So if there was an edge between, let's say there was 0, 4, 3 and 4, which would constitute a cycle, right? And now we check here 3, the parent is 0, and 4, the parent is 0, so they have the same parent. That means we have a cycle, right? So whenever basically during union operation, we find that the set representative or parent, or whatever you want to call it, is the same for the two nodes we are trying to union. Then that means we have a cycle, because otherwise they won't be in the same cycle. If they won't be in the same set. Being in the same set means they were already connected, and now we found a new way to connect them, so that's certainly a cycle. So let's implement this. And so the way to implement this is we are going to have also, of course, the union and find operation. And then we need to construct, as we said, every node first is going to be its own set. That's what we said here. And so we need to do that. So let's say first parent list. And so that's just range of n, which means parent of 0 would be, so that's the list of parents, 0, 1, 2, 3, 4 until n. And we are going to define a find operation and then a union for x and y. And at the end, of course, we are going to check edge is equal to n-1, and then the other check needs to be that there is no cycle. And so what does find operation do? So find operation first checks that the parent of x is, if it's equal to x, that means we should just return x, right? So we find the parent. Otherwise, we need to find the parent of x. So that means return this. And then for the union, we are going to get the parent of x and y. So find x. So let's say parent of x and parent of y would be find x and find y. And we are going to check, as we said, so here we found the representative of each set, of the set that contains x and the set that contains y. If they are equal, that means they were already connected in another way, so we need to return that there is a cycle. And so let's just return that there is a cycle, which is true. So union and return true if there is a cycle. So the union operation allows us to detect if there is a cycle. So here, that means cycle detected. And otherwise, we can just like link them. So we say parent of, so the parent of px is going to become py. That's what union means. So we take a parent of one of them and we attach it to be y, and to be the other one. That's pretty much it. So this one range is going to say this. And now here we need to check, we need to do union on all of them. So let's just say, so we need to go through all edges and do union on them. So basically that means for E in edges, let's call it UV, we are going to check if, we are going to union them, and if UV is true, then return. So here we need to return false, otherwise, right? So if it returns true, that means we have a cycle, and so we need to return false. This is an out of valid tree. So this means there is a cycle. Otherwise, we are good and we can just check the last one. Pretty much, yep. So this should work normally. So let's run it. Okay, so that passed. So this is using union find. To check the cycle, we just do the normal union find operations, and then we go through all edges and union each of them. Any edge, any two vertex in this linked with the same edge, we do a union operation on them. And whenever we find that those two new vertices in the new edge are already in the same set, that means we have a cycle. And yeah, so that's it for this problem. We solved it with different approaches, and hope it was useful. Thanks for watching. See you next time. Bye.